So now we move on to our second unit, and you can see on the title of the sheet that I gave you, we're going to be dealing with a completely different branch of mathematics than we previously were. We're going to be dealing with mathematical objects called groups. You didn't know this, you had no real reason to know this, but when you did algebra, when you learned algebra, you were learning something about groups unintentionally and working with them. So we're going to talk a little bit more in a more general approach. So today is just going to be a little bit about the properties. Okay, so just to give you a little insight, when we come back next time, so next week on Monday, we will have more, there'll be more nuts and bolts, that there'll be some tables and things like that. So this actually, I think, is a pretty fun unit. Today might seem a little drier, but when we come back next week, it spices up. So just trust me for a minute on that. So before we talk about what a group is, we got to talk about this first thing. We have a definition. We're going to define something called a mathematical system. So just so that you have something to do, here is a blank. A mathematical system consists of two things. It consists of a set of elements, and it contains at least one what's called a binary operation. Okay, I'll define what a binary operation is in just a minute. Okay, you know what binary operations are. That's just a fancy math word for something you already know how to do. So a mathematical system, which is what we're talking about in this unit, mathematical system has two things. It has a set of elements, and it has at least one binary operation. And what a binary operation is it is a rule that can be performed on two elements of a set. So after this, I'm just going to define for you a couple of different mathematical systems so you can see that you actually do have some experience in this. We're just giving some names that you've never heard before to things that you've already seen. So the first example is going of my set of elements in my binary operation is going to be first the whole numbers. Okay, whole numbers are, I'm going to show you what the set is. The whole numbers are these numbers. They start with 0 and then go 1 and 2 and 3 and 4 and 5 and 6. And then I'm going to put some dots because I'm tired of writing. So that is my set. And then the binary operation, again, fancy word, the binary operation is addition. So I'm just going to put the words right here underneath that that's our binary operation is addition. So what I mean by binary operation of my set of elements is I can take any two elements of the whole numbers and I can add them together. I've just defined for you a mathematical system, addition in whole numbers. Something you did way back in elementary school is really what's called in math lingo, a mathematical system. And so in this first section, we're doing sets of elements that are very large, infinite sets. That's why I have this ellipsis here. This ellipsis tells me, in case you don't remember or you never knew what that was called, these three dots are called an ellipsis. And the ellipsis just tells us to keep following that same pattern because the whole numbers go on forever and ever and ever and ever. So we're dealing with infinite sets in this unit. When we come back next week, we'll be talking about finite sets. That's where this whole idea of mathematical systems gets a lot more fun and we get more things that we can do. Second mathematical system that I'm going to tell you about is multiplication on the rational numbers. Rational numbers, again, are fractions, in case you don't remember that terminology. So my set of elements are the rational numbers. Now I can't make a list of the rational numbers, so I am going to just I'm just going to show you how we write this mathematically. If you did take 1106, then this notation will look familiar to you. If you didn't, then I'm just going to do my best to do this. So this is called set builder notation. Rational numbers are fractions. So anything that I can write as A over B. So that's an A in the top, B over the bottom. And I'm keeping this nice and general. I'm trying not to get too technical because it is not a prerequisite that you've taken MGF 1106. So the truth about A and B is that A and B are integers. There's one other constraint. Hey, I did. Let's change that to R. Thank you. They sound similar. Okay. A and B are integers, and B can't be 0. We can't divide by 0. So this is how we write out the set of the set of rational numbers. In case you don't remember what a rational number is, let me over on the side give you some examples. Okay, I don't want to make any assumptions here. Examples of rational numbers are like a half, or like 3/5, or -9/4, or the number 7, because we could write that as 7/1. Those are all examples of rational numbers. Notice I've just taken two integers and I have stacked them. Okay, so this is just fancy lingo for take any two integers and stack them. And what makes this a mathematical system is my binary operation is multiplication. Then one more mathematical system, just so that I am covering a bunch of bases and giving you good examples. I hope that that's good. Is subtraction with the integers. So my set of elements is the integers. Again, I'm just trying to remind you of some things that you may have long since forgotten or has been dormant in your brain for a while. So the integers are the whole numbers like we mentioned before. So 0, 1, 2, 3, 4, 5, and then an ellipsis. And then backwards, we have -1, -2, -3, and now I'm out of room, so I'll put another ellipsis. So the integers extend in both directions, like the number line extends in both directions. And what defines and what makes this a mathematical system is I've got the binary operation of subtraction. So all I've done there, I've just defined for you, because I defined this word mathematical system. I have given you 3 examples of what mathematical systems look like, just so that you can begin to get some experience. Because I'm pretty sure, I'm 99.99% sure, none of you have dealt with or thought about or even knew about this thing called a mathematical system. And that's why we're here and we're learning about it today. So what we're going to do is we're going to go through and we're going to talk about some properties that mathematical systems may or may not have, so that I can get to the end goal and to talk about this mathematical object called a group, which is going to be of interest to us in this second unit. So the first property. Okay, if you took any algebra, then these first two I know that you've seen, whether or not you could tell me what they are. The first one is the commutative property. Okay, I'm just going to deal with addition and multiplication here, because those are the ones that the commutative property applies to. And so maybe somebody remembers, if I say A plus B equals, does anyone remember what the commutative property tells me that's equal to? C, it could be equal to C. That's a little bit of algebra. But for the commutative property, yes, thank you very much. That is great. In case you didn't know that, the word commute, when you commute to work, what do? You go back and forth, right? That's what the word commute means. So we see that in the word commutative. And so it just means A plus B is going to be equal to B plus A. The order does not matter. Okay, so the commutative property says that I can add two numbers in any order, and we are good. And then the same thing's true for multiplication. If I have A times B is equal to B times A. Fantastic. Here's a question. I mentioned at the beginning that I'm only talking about addition and multiplication, because those are the only ones that the commutative property applies. So here's my question. Is subtraction commutative? Well, yes, if you're paying attention. He said no. Give me an example of how we know that. Go ahead. Well said. Excellent example. There is the definitive example of why we know right away subtraction is not commutative. If I take 5 minus 3 and then flip it around, 3 minus 5, those are completely different things. And so subtraction is not commutative. So great, good answer. And we could do the same thing for division. 2 divided by 1 is not the same thing as 1 divided by 2. Those are completely different things. Okay, so commutative properties just apply to addition and multiplication. Associative properties. Again, if you took algebra, I know that you've seen this. I am just thinking that I'm reminding you of this. Associative, when you associate with something, it means you are grouped with something. So the associative property has to do with grouping. So what this means is this. If I have A plus B in parentheses, if I have them grouped together, and then I add something plus C, then notice I'm not going to change the order of the 3 things right there. I am just going to change the grouping. So I'm going to have the A first still, plus, and then the B plus C is in parentheses. So notice the A, the B, and the C, the A, the B, and the C are in the same order both times, but I have changed what the grouping is. So that what the associative property says is, doesn't matter how you group it, both those things are the same. Same thing's true for multiplication. Again, notice when I write down these terms, the A times B times C are all in the same order. I've not applied the commutative property. Nothing has been commuted here. I've just changed the grouping on both sides. So I've kind of spoiled example 4 with this, but we're just going to do a few examples just so that we can get our feet wet with the commutative and the associative property. So example 4 says, what operations on integers are commutative and associative? Well, I've already told you. Addition and multiplication are both commutative and associative. So all I want us to do here is just make up a few examples. Pick, for the commutative property, pick a couple numbers A and B and just prove to yourself that they are both commutative. And then pick 3 numbers and do the same thing for the associative property. I'm gonna doodle up here the same thing just so that you see what I want you to do. And this is just us getting some experience and verifying for ourselves that we see that adding and multiplying are commutative and associative properties. So in case, again, you're confused about what I'm asking you to do, I've just done this for 5 and 6 for multiplication. I'm going to pick 2 different numbers. I'm going to do it for addition. Okay, so keep working. I'm just going to explain to you what I did here. So I've done this with adding and multiplying for my commutative properties. I did 5 times 6 is 30, 6 times 5 is 30. There we go. Those 2 things are equal. And so that is just a demonstration. It doesn't prove anything, but it's a demonstration that the commutative property holds for multiplication. Then I took 7 plus -4, I got 3. And then -4 plus 7 is 3. So again, I can commute addition and get the same thing. So those 2 things. Over here for the associative property, I took 8 plus 6 inside the parentheses, then I'm going to add to that -2. Again, I know this is going in your way back machine, but when you do your order of operations, you do what's in parentheses. So the 8 plus 6 is 14. So I have 14 plus -2 gave me 12. So now I'm just changing the grouping over here. So I'm pulling the 8 out of the parentheses, and now the 6 plus -2 are in. So 6 plus -2 is 4. And 8 plus 4 is 12. I get the same thing regardless of the grouping. And then I did the same thing for multiplication. So all I asked you to do there was just to make up a couple of examples, because what I will be asking you on the next test, I'm not going to ask too much detail about this, but I am going to ask you to highlight what's the associative property say, what's the commutative property say. You're going to have to give me an example. It's going to be part of what we do. Okay, so these things will pop up again. Any questions so far? Got some definitions going on. Like I said, today's a little bit of a dry day, but we need this information if we're going to have any fun in the other sections. Questions, comments, concerns so far? All right. Well, then those are the first two properties. You may have heard of those first two properties. My expectation is the next one you probably have not heard of, so that's fun. Property called the closure property. Okay, so closure, this is not like a relationship where you got to get closure. This is math. So closure property says this: if you do a binary, if a binary operation is performed on any two elements of a set, and the result is an element in the set, that set is closed. That's what closure means. It's closed under the operation. So what that means is if you take any two elements of the set and you perform the operation, whether it's addition, whether it's multiplication in this case, and you get another element of the set, it's closed. If you get something outside of the set, it is not closed. Okay, it would be called open, but we're not interested in those in this section. So my first question, example 5, is: are the whole numbers closed under addition? Well, I want you to just think about this. Write down the whole numbers. You saw them on the front page. Add a couple, and I want you to come up with a hypothesis. Would you answer yes or no? Are they closed? Don't shout it out. I'm going to give you 30, 40 seconds to think about it. Pick a couple whole numbers, do it a couple times, and add them up and determine, do I always get another whole number when I add two? All right, so I've written down the whole numbers right here. The whole numbers start with the number 0, and then you count by ones forever and ever and ever. So what I've asked is, are the whole numbers, do we suspect that they are closed or not? So somebody give me two whole numbers. What do you got?
0 plus 5.
0 plus 5. When I add 0 plus 5, we get 5. Is this result right here, is this a whole number? Yes, it's in the set. Check. Okay, give me another example. Okay, 6 plus 8. 6 is a whole number, plus 8 is a whole number. 6 plus 8 is 14. Is 14 a whole number? Yes, let's do one more, and then you're going to give me your hypothesis. Give me another pair of whole numbers. What do you got? 5 and 12. Lovely. 5 plus 12. 5 plus 12 is 17. Is 17 a whole number? So, again, we're not proving anything because we don't have I don't even have the mathematical capacity to prove it, but we have demonstrated. What is your suspicion? Are the whole numbers closed under addition? Yes or no? Yes. Anytime you pick two numbers in the whole numbers and you add them, you are going to get another whole number. So the answer to this is yes. The whole numbers are closed under addition. Great. Well, now I'm changing the mathematical system. In example 6, are the whole numbers, which we were just dealing with, are they closed under subtraction? Okay, so what I would like you to do is pick a couple pairs of whole numbers and subtract them. Am I always going to get another whole number when I subtract? And so that's going to be the question we answer in about 30 or 40 seconds. right, so again, the whole numbers start with 0, go up, counting by ones forever and ever. So somebody give me 2 whole numbers to subtract.
8 minus 3.
Okay, 8 minus 3, those are both whole numbers. 8 minus 3 is 5. Is 5 a whole number? Yes, so far this looks okay. Somebody give me another pair. There you go, 2 minus 3. 2 and 3 are both whole numbers again. When I do 2 minus 3, what do I get? Uh-oh. -1. Is -1 a whole number? No. I'm going to cross that. So do I always get a whole number when I subtract 2 other whole numbers? No, I do not. Okay, so are the whole numbers closed? No. Does everyone see the difference between those two things? Because I know this is difficult stuff. Okay, so questions are totally appropriate on this. Okay, or like they're always appropriate, but I know even more so now. All right, we're going to do one more. Let's change that mathematical system just a little bit. So this time, instead of are the whole numbers closed under subtraction, are the integers closed under subtraction. So the integers, remember, are the numbers that go in the negative direction and the positive direction, counting by ones forever and ever. So what I would like you to do is what we've done a couple times, pick a couple different pairs of integers and subtract them, and we're going to answer this question. All right, so we're going to subtract some integers. Somebody give me a pair of integers to subtract. -4, that's an integer, minus -3, that's an integer. Now, if you remember your subtracting, when you subtract the negative, when you have those two negatives, what does that become? An addition. So I'm going to rewrite that. If you don't need to rewrite that, that's fine. -4 plus 3, and that's -1. Is -1 an integer? Sure is. Let's do another one. Give me another pair of integers. 1 minus -4. And again, when I subtract the negative, that becomes a positive. So I'm going to just write that down. And 1 plus 4 is 5. Is 5 an integer? Yeah, don't be shy. It sure is. And we could do that over and over again. What's your suspicion? If I subtract 2 integers, do I always get an integer? Yes, I sure do. So I'm going to write the word yes. The integers are closed under the operation of subtraction. Okay, before I move on, I don't want to move on too quickly. Does everyone understand or does right now grasp this idea of closure? What does it mean for my set to be closed with an operation? We good? Okay, because that'll come, all of these concepts are going to come up over and over in this unit as we are doing things. So I just want to make sure I'm doing a decent job explaining these things that are likely unfamiliar to us. Okay, the identity. Okay, the next thing, this is the 4th of the 5 properties that we're going to talk about. So we did the commutative property. I can change the order of 2 elements. The associative property, I can change the grouping of 3 elements. And then closure. When I do the operation on any 2 elements, I always get another element in the set. So the identity is the 4th one. And the identity says, given an element in the set, an identity is an element that produces the given element when the binary operation is performed. I probably should have made that blank bigger. Sorry. Now that's a lot of words for something that I think you're gonna think is pretty easy. So example 8. What is the identity for integers under addition? So what I'm asking is if I start out with the integer, let's say 7, what do I add to 7 in order to end up with the identical thing? What's the identity for addition? 0. Okay, so 0 is the identity for addition. which is something you knew. You might not have known it was called the identity, but I am pretty sure that I could have said to anybody in here, if I take any number and add 0 to it, what do I get? I get the same number. That's what it means to be the identity. Okay, so 0 is the identity. I'm just putting words to something that you know as common sense. So then here's my next question. I'm going to give you 30 seconds to think about it. Example 9. I want you to write down what you think the identity for integers is under multiplication. So if I start off with any integer, let's say -9, what am I going to multiply by -9 in order to end up where I started? And the identity is what? 1. Yes. Again, I'm teaching you the word identity here. You knew if you had walked into class today and my first question had been, if I start with any number and I multiply by 1, what do I get? And you would have said, I am sure you get the number you started with. That's what it means to be the identity. Okay. Now for multiplication and addition, you already know the identities. You can take those for granted. You don't ever have to prove that to me or tell me that. If I ask you what the identity is for addition, you're just going to tell me 0. Where this is going to come up though, is when we come back next time, we're going to talk about mathematical systems that we define by a table. That's where it gets fun. We're gonna have a good time. And then we're gonna look for identities and we're gonna look for, is it closed and things like that. And so it'll be, that's where this unit actually gets really interesting. Did you have a question over here? Does somebody raise their hand? Oh, yeah, we hate that. All right, inverses. Okay, 2 elements in a set are what's called inverses. If the binary operation is performed and the result is the identity element. Okay, I know, again, that's a lot of words. So I'm gonna do a couple of examples with you here in a minute to illustrate what it means for 2 things to be inverses. So 2 elements in a set are inverses if the binary operation is performed and the result is the identity element. Okay, so what does that mean? Let's make this a little clearer. So example 10, does every integer have an inverse under multiplication? Well, we'll come back to that one. That's actually not the one that I would have started with. Let's do these in reverse order. Example 11, does every integer have an inverse under addition? Okay, so what does it mean for things to be inverses? Well, remind me, because we just defined this, what is the identity under addition? Okay, the identity, that's on the previous page, is 0. Okay, so what I'm asking you here is this. If I take -9, what do I add to -9 in order to get 0? Meaning, what's the inverse of -9 under addition? +9. Yes, that's the inverse. So I'm just going to write under here, these 2 numbers are what we would say are inverses. -9 plus 9 is equal to 0. So let's now go back to example 10. Oh, example 11. What's the answer? The answer is yes. In the integers, every inverse is included in the integers because -9 goes with 9, -40 goes with +40. Those are all inverses under addition. Now here's the key in example 10. We're talking about the set of integers. So here's what I want to know. If I start with the number, let's say 2, what do I multiply by 2 in order to get the identity under multiplication? Well, let me define what is the identity under multiplication that we just saw. Okay, the identity is 1. So what do I multiply by 2 in order to get 1? Perfect, a half, 1/2. So an inverse exists But here's the problem. I asked you for the integers. Is a half an integer? No. So this is not an integer. Okay, a half is not an integer. So that's why I'm going to answer this question no. Now, if I talked about the rational numbers, if I talked about the set of fractions, the answer might be a little different, okay? But these two things, they are inverses. The problem is that the inverse is not a part of the set that we were talking about, okay? So I will write right here that these two things are indeed inverses of each other, but a half is not an integer. By the way, in case you remember, in case you remember your arithmetic, does anyone remember the word for if you take a number and you flip it over? The reciprocal, yes. So as far as multiplication is concerned, reciprocals are inverses, just a different word that means the same thing. Okay, well, we are there. We are ready to define this thing called a group. That was my promise to you when we started the section. That's what we're going to spend a lot of time talking about in this unit. So the properties of a group. So a mathematical system, okay, mathematical system is what we've been talking about. A mathematical system is a set and a binary operation. A mathematical system that meets the following four requirements is called a group. Okay, this is a special mathematical object that has good properties that are that make it fun to use and have application when it is a group. The first thing, so when we do our check of some mathematical systems, the first thing we're going to look at is it closed? If a mathematical system is closed, it has potential to be a group. But as we saw, not all mathematical systems are closed. If I had the whole numbers and subtraction, that mathematical system was not closed. It would not be a group. You can answer no right away. Once you answer no to one of these, you don't have to go any further. The second thing that a mathematical system has to have, if it's going to be a group, is that it has to have an identity. So is there an element that under the binary operation always produces the original element, as we just saw? So for addition, that's 0. For multiplication, that's 1. Is the identity part of the set? The third thing is that every element has an inverse in the set. So for like example 10, if we slide the paper back up, for example 10, it's closed. If I take any two integers and I multiply them, I get another integer. Good, it's closed. It has an identity because 1 is an integer. Okay, so the identity is part of the set. But where it fails is every element does not have an inverse that's in the set, which is what we saw right here. A half is not in the integers. So this example 10 would not be a group. Can't be. Okay, so it's a mathematical system. That's great, but it's not a group. And then the fourth thing is that the associative property holds. So for what we've been talking about so far, if I define for you a mathematical system with subtraction or division, you know right away it's not going to be a group, because subtraction and division are not associative. So for our purposes in this section only, the associative property holds. We know that holds for addition and multiplication. Okay, you can take that to the bank. One more little detail, and then we're going to finish our time in this section with 3 examples. And so a specific type of group that satisfies the commutative property. So if I could have a number 5 and it was the commutative property also holds, then that is called a commutative group. There's actually another word for it called an abelian group. You don't need to know that. I don't know if my math lab uses that. That's named for the mathematician who got drunk one night and thought all this up. Okay, so I don't know that he got drunk, but I would think it had to be doing something because it's wild stuff. All right. So what we're going to do, how we're going to end our time as far as this section is concerned, is we're just going to start with some mathematical systems, and we are going to determine yes or no, is this mathematical system a group or not. I will on the test, okay, so just so that you know, I will put one problem like this. It's the first problem on the test is going to be to determine if a mathematical system that is infinite like this is a group. Okay, so the reason I put it on there is it just means that it allows me to see, do you remember these properties? Okay, so just FYI, there's going to be a problem like one of these last three that's going to be on the next test. So after you do your homework, if you still are not super clear on what's going on, we can do another example. So I will do example 12 with you. Determine whether the mathematical system consisting of whole numbers and addition. So let me write down the whole numbers again. And addition, okay, that's my mathematical system. I want to know, is this a group? Okay, fantastic. Let's start off. Step one. Is it closed? Well, we answered this question earlier. When I add any two whole numbers, do I always get a whole number? Yes. So all I'm going to ask you to do here is just write down an example for me. Okay, or a counter example if it's not true. So for instance, 7 plus 8 is 15. And so that leads me to believe, yes, it is closed. That was a previous example. So we're 1 for 1. Is it a group? Not yet, but it could be. Let's do 2. Number 2 is, does the identity exist in the set? Okay, what is the identity for addition? 0. Is 0 a whole number? Yes, 0 is a whole number. Great answer. Love it. All right, we're 2 for 2. Is it a group? Well, I don't know yet, but it's closer to being 1 than it was before. Step 3. Every element has an inverse in the set. Okay, well, pick a whole number for me. 4. We know for addition, what is the inverse of 4? -4. Is -4 a whole number? Okay, so I'm just going to draw a little arrow. This is not a whole number. So is the inverse in the set? The answer to that is no. I'm going to circle it because that is important. So I don't even need to go any further. Are the whole numbers under addition a group? Well, the answer to that is no, it's not a group. It failed step 3. If step 3 did satisfy when you get to step 4, well, we know, because I already told you that addition is associative. All I would ask you to do, and I'll guide you through this on the test, what I would ask you to do is give me an example of the associative property. I just want to know that you remember what that is. Okay, so you can take to the bank that addition and multiplication are associative. Okay, you don't have to prove that or question that. That is given information. All right, so here's what I would like to do. Example 13. I want you to give your best shot at this. I'm going to help you firstly by defining the set. Okay, the set says, are the positive rational numbers under multiplication a group? Okay, so remember, rational numbers are fraction. So are positive fractions under multiplication a group? So examples of positive fractions are like 1/3, 4/9, 5/6. Remember, you can't list them because there's lots and lots and lots of fractions. I'm just giving you some examples. 7/4. Okay, I could give lots and lots of examples. 0, by the way, is not positive. 0 is not positive or negative. So when you are doing your homework and it says positive rational numbers or negative, I'm just going to write exclude 0. 0 is not considered a positive number or a negative number. So, all right, so give it a try. Do your best. Do you think that this is going to be a group, yes or no? So do your 4 steps and we'll see. We'll compare notes in 2.5 minutes. Right. So I just want to let you know, this is a difficult thing to do. So if you didn't get all the way through, it's okay. Okay, we're learning, we're developing clarity. You're going to do your homework. You're going to come back with questions. Okay, so I don't want you to sit here and think that I'm thinking this is an easy thing. I think this section 9.1 is one of the harder sections in our whole class. Okay, I think the sections that come after this in this unit get progressively easier, but we start off with the gusto here. So just so you know. Okay, so step number 1. Is this closed? Are the are the positive rational numbers under multiplication closed? Well, let's pick a couple of positive rational numbers. Somebody give me a couple of positive fractions. 2/3 times 4/3. Now, maybe you forgotten how to multiply fractions. You multiply fractions just by going straight across the top, straight across the bottom. Okay, that's how you multiply fractions. So when I do this, 2 times 4 is 8. 3 times 3 is 9. Is 8/9 a positive fraction? Yes, let's pick another pair just to get just to make sure that we're certain. Somebody else give me another pair of positive fractions.
7/15 times 3/5.
Okay, 7/15 times 3/5. So 7 times 3 is 21. 15 times 5 is 75. I could reduce that a little bit. I'm not worried about that. We'll just keep it like it is right now. Is 21/75, is that a positive fraction? Yes. So if I take two positive fractions and multiply them, do you think I always get another positive fraction? Yes. Okay, so far we're good. It's closed. All right, step 2. Step 2, does the identity exist in the set? Well, as I'm writing this down, what's the identity for multiplication? 1, we already know that. Is 1 a positive fraction? Yes, 1 can be written as 1/1. Okay, so 1 is a positive rational. So it's in the set. So yes. Okay, so we're doing good. Step 3. Does every element have an inverse? I'm just rewriting these because it helps us remember what they are. So every element has an inverse. So earlier, let me pull out that example from earlier. I said 2 times what gives us the identity of 1, and the answer was a half, which is also the reciprocal, which we said. Are both of these numbers positive fractions? Yes. So give me another number, another positive fraction. 2/3. What would I multiply 2/3 by to get 1? Well, yes, you already gave the reciprocal. You flip it over. Love it. 3/2. So whatever fraction you picked, if you didn't know what the what the inverse was, it's just the reciprocal. Flip it over. So if you've got 4/11, then the inverse is 11/4. Okay, if you've got 7/112, it's 112/7. You just flip it over. So are both of these numbers here positive fractions? Yes. So does every element have an inverse that's in this set? Yes. Last but not least, associative property. Well, I already told you, is multiplication associative? Yes. So all I want you to do, and if you didn't do this, that's okay. You'll do this on the next problem if we get that far. You're just going to give me an example. So I need a little more room because I'm writing very large. So I'm just going to continue down here a little bit. Here's my example. Okay, so this is not part of example 14. This is part of 4. So give me 3 positive fractions. Okay, a half, and a quarter, and an eighth. Great. So I want to know, is a half times a quarter times an eighth, does that equal a half times a quarter times an eighth? I'm just giving an example so that I know that you know what the associative property is. That's the whole purpose to this right here. You can take to the bank. We know that multiplication is associative. So you're just giving me an example that you know what the associative property is. Okay, so on the left side, a half times a fourth. In the top, 1 times 1 is 1. 2 times 4 is 8. And then again, 1 times 1 is 1. 8 times 8 is 64. When I do it the other way, and with the 1/4 and an eighth, I have a half times 1 times 1 is 1. 4 times 8 is 32. And then 1 times 1 is 1, and 2 times 32 is 64. And look at that. It's the same, just as I knew it would be, because multiplication is indeed associative. So example 13, are the set of positive rational numbers under multiplication a group? Yes, it's a group. And I'm going to be excited about it. I'm going to put a couple exclamation points. Whoops, you didn't see any of that because it's off the screen. But yes, it's a group with exclamation points because we are excited because that was a difficult problem. All right, one more example of this. Example 14, you're going to do the same thing for me. you're going to go through the steps and determine if the integers under addition form a commutative group. So it's the first 4 steps that we just did. And then step 5 would be the commutative property. So don't worry about the commutative property just yet till you get to the end. So example 14 are the integers under addition. First, are they a group? And then we'll see if they are a commutative group. Okay, again, hard problem, lots of detail here. That's why you'll do some homework and practice. I think there's only like 10 or 11 homework problems. So you'll get lots of different opportunities, or at least that many different opportunities to practice. And again, when you come to class, if you have a question, take a screenshot, take a picture with your phone, or email me the screenshot so that we can do any problems that are causing you undue trauma. Okay, so the first thing is this closed? I believe this is a problem we did earlier. If I take any 2 integers and add them, do I get another integer? So I'm just going to pick an example. So if I take -7 plus 16, those are both integers. And -7 plus 16 is 9. 9 is an integer. Any example that you have out there should do the same. And so, yes, the integers are closed under addition. The second thing is, does an identity exist? All right. Well, we know we've answered this a bunch of times already. What's the identity for addition? 0. Is 0 an integer? Yes, it is. Okay, so 0 is an integer, so we're good. We're 2 for 2. Zero is an integer, so yes. So number 3. I want to know, does every element have an inverse in the set? So if I pick any integer, so again, let me pick -7. It was on my mind earlier. What is the inverse of -7 under addition? +7. Okay. Are those both integers? Yes. How about my other one that was from my example, 16? What is the inverse of 16? Is that an integer? Yes. So does every element have an inverse in the set? Well, the answer to that is yes, it does. The fourth thing is it associative? Well, again, I've given you this information to take to the bank. Is addition associative? Yes, it is. So let's just give an example. So whatever 3 integers you picked, it absolutely does not matter. So if I pick 8 plus 6 plus -5, or 8 plus, and then the 6 plus -5 is in parentheses. On the left, 8 plus 6 is 14. 14 plus -5 is 9. And on the right, 6 plus -5 is 1. Plus the 8 outside the parentheses is 9. That should always work out because I've told you that addition is associative. So we have a group. Woohoo! At this point, we know we have a group. So we can go to the last part of this. You can't be a commutative group if you're not a group. Okay, so if at any point we have failed, the answer is no. You have to first be a group before you can do step 5. And the step 5 is it commutative? Well, again, I told you could take this to the bank earlier. Is addition commutative? Yes. So let's just give an example of the commutative property. And so hopefully you just said, okay, I'm going to pick my favorite 2 integers. Mine are 3 plus 7. And so is that going to be equal to 7 plus 3? Well, I sure hope so, because the Perkster told me in class that addition is commutative. And there we go. So are the integers a commutative group under addition? And the answer to that question is going to be yes, they are.